This is Mrs. Zappia with Lesson 8, the difference between theoretical probabilities and estimated probabilities. Student outcomes for this lesson. Given theoretical probabilities based on a chance experiment, students describe what they expect to see when they observe many outcomes of the experiment. Students distinguish between theoretical probabilities and estimated probabilities. Students understand that probabilities can be estimated based on observing outcomes of a chance experiment. Pause the video and copy the essential question for this lesson. Is there an exact number of times you should toss a coin to estimate the probability of getting tails? Explain. Did you ever watch the beginning of a Super Bowl game? After the traditional handshakes, a coin is tossed to determine which team gets to kick off first. Whether or not you are a football fan, the toss of a fair coin is often used to make decisions between two groups. Examples 1 through 9. Why a coin? Coins were discussed in previous lessons of this module. What is special about a coin? In most cases, a coin has two different sides, a head side and a tail side. The sample space for tossing a coin is heads or tails. If each outcome has an equal chance of occurring when the coin is tossed, then the probability of getting heads is 1/2, or 0.5. The probability of getting tails is also 0.5. Notice that the sum of the probabilities is 1. The probabilities formed using the sample space and what we know about coins are called theoretical probabilities. That would be a good thing to highlight. The theoretical probabilities. That is the probabilities formed using the sample space and what we know about coins. Using observed relative frequencies is another method to estimate the probabilities of heads or tails. When they talk about using observed relative frequencies, that just means looking at the results of an experiment. A relative frequency is the proportion, so it's a fraction, derived from the number of observed outcomes of an event divided by the total number of outcomes. A relative frequency is the proportion derived from the number of observed outcomes of an event divided by the total number of outcomes. Recall from earlier lessons that a relative frequency can be expressed as a fraction, a decimal, or a percent. Is the estimate of a probability from this method close to the theoretical probability? The following example investigates how relative frequencies can be used to estimate probabilities. Beth tossed a coin 10 times and records her results. Here are the results from the 10 tosses. The total number of heads divided by the total number of tosses is the relative frequency of heads. Let's write that down. The relative frequency of heads is equal to the total number of heads divided by the number of tosses. And we'll be doing this skill several times during this lesson. It is the proportion of the time that heads occurs on those tosses. The total number of tails divided by the total number of tosses is the relative frequency of tails. Beth started to complete the following table as a way to investigate the relative frequencies. For each outcome, the total number of tosses increased. The total number of heads or tails observed so far depends on the outcomes of the current toss. Complete the table for 10 tosses recorded above. So in your book, this is on page 53. I've taped it up here to the top of the page so that we could look at it. So if we look at the result of the first outcome was heads, and that's written here. So the number of heads so far is 1. The relative frequency is 1 head over 1 toss, and 1 divided by 1 is 1. The total number of tails so far is 0. 0 tails divided by 1 toss equals 0. In the second row, heads was tossed, so we recorded heads as the outcome. The number of heads so far is 2. That's 2 heads out of 2 tosses, and 2 divided by 2 is 1. We still have 0 tails so far. Now it's 0 tails divided by 2 tosses, and that equals 0. Toss 3, we have tails. So the outcome is tails. The number of heads so far remains at 2. So we have 2 heads divided by 3 tosses, and 2 divided by 3 rounds to 0.67. We're going to be rounding today to the nearest hundredth. The number of tails so far. So we got tails on that toss, so now we have 1 tail. The relative frequency of tails is 1 tail over 3 tosses. 1 divided by 3 is 0.33 repeating, which rounds to 0.33 or 33 hundredths. The fourth toss is heads. The number of heads so far, so we're going to add 1 more to that and we'll get 3. Now we have 3 heads over 4 tosses. And 3 divided by 4, you might know that already, is 0.75. The number of tails remains at 1. So we have 1 tail over 4 tosses, and that's 0.25. So we have a denominator of 1 because there was a 1 toss, 2 for 2 tosses, 3 for 3 tosses, 4 for 4 tosses. So that's where the denominator is coming from. The numerator is the number of tails that we've had so far. Since we had heads, we had 0 tails, 0 tails, and here we tossed a tail, so now we have 1 tail. And then this was heads, so it remained at 1 tail. So if you're ready to complete the chart on your own, pause the video and continue to complete the entire chart. All right, let's get back to this. So on the 5th, we have heads. That's 4 heads. So now we have 4 heads out of 5 tosses. 4 divided by 5 is 0.8. And our number of tails remains the same at 1. 1 divided by 5 tosses is 0.2. So I'm going to go ahead and fill in the rest of the chart. But I'm not going to do the decimals. I'd like you to go back and do the decimals on your own. You can either follow along or you can skip ahead and do this on your own. So number 6 is heads, number 7 is tails, number 8 is tails, 9 is tails, and 10 is heads. So that's 5, and now we have 5 out of 6. And this remains at 1 out of 6. Tails, so this remains at 5 out of 7. And now we have tails, so we have 1 more tail. Now we have 2 out of 7. Tails, this remains at 5, so we have 5 out of 8. And this is another tail, so that increases to 3 out of 8 tosses. And now we have another tail, so that remains at 5. Now we have 5 out of 9. Another tail adds up to 4. Now we have 4 out of 9. And finally, another head, and that gives us 6 heads and 6 out of 10 tosses. And then tails remains the same, and now we have 4 out of 10. So pause the video and complete the division to fill in the rest of the chart. Remembering to round to the nearest hundredth. Now just take a minute and double check your decimals to make sure that you've done the division correctly. Question 2. What is the sum of the relative frequency of heads and the relative frequency of tails in each row of the table? So in row 1, the relative frequency of heads is 1 and the relative frequency of tails is 0. In row 2, the relative frequency of heads is 1, the relative tails of frequency, you know what I meant, is 1. In row 3, the relative frequency for heads is 0.67. And the frequency of tails is 0.33. And go ahead and add that together. and you should have gotten 1. Row 4. The relative frequency of heads is 0.75. The relative frequency of tails is 0.25. And the sum is 1. At this point, you might be thinking, is it always going to be 1? That's a good question. Go ahead and complete the table and just use your calculator and check and see if there are any rows that don't add up to 1. So you may have noticed that in every row, the relative frequency of heads plus the relative frequency of tails is equal to 1. In question 3, Beth's results can also be displayed using a graph. From the table above, complete the graph below using the values of relative frequency of heads so far. The table is on page 54 in your book. I have copied the table on this page to make it easier. So if you want to highlight the column in your paper, feel free to do that. All right, so notice that the first 3 points are graphed. Let's just go over how they did that. So here, the number of tosses is on the x-axis. So we have 1 toss, and the relative frequency is 1, and there's the point. I'm going to delete these highlights after we do them. Then the second toss is here, and the relative frequency is here. The third toss is here, and the relative frequency is 0.67, which is more than 6 but less than 7. So our next point is going to be the fourth point along the x-axis, and then we'll follow it up to 0.75 on the y-axis. So 0.75 is right about here. So I'm just going to go back and erase these other highlights now. And we'll continue to graph this data. Feel free to pause the video and graph it on your own. 0.5 is at 0.8. Toss 6 is at 0.83, which is just a little bit higher. Toss 7 is at 0.71. Toss 8 is at 0.63. Toss 9 is at 0.56. Toss 10 is at 0.6. And then you can go ahead and connect the lines as they have done on their graph. And that is what our graph looks like. What I want you to notice on the graph is the first toss. Notice that the first toss had a 1 right here. If the first toss was a tails, then this first toss would be marked down here at 0. So the first toss is either going to be at 1 or it's going to be at 0, one or the other, because it's either heads or it's not heads. And then it remained at 1 because the next toss was also a heads. Then it dropped because when you got a tail, the relative frequency dropped because it was 2 divided by 3 instead of 3 divided by 3. Beth continued tossing the coin and recording results for a total of 40 tosses. Here are the results for the next 30 tosses. As the number of tosses increases, the relative frequency of heads changes. Complete the following table for 40 coin tosses. So the number of coin tosses, this is already determined for the first 3 rows, for 1, 5, and 10, and that data can be found on the previous page. The data from this row. And the row 4 will be the data from this row. And for row 10, it will be the data in this row. So I'm going to go ahead back and fill that in now. Okay, so for 1, the number of heads so far was 1, and the relative frequency was 1. In the after the 5th toss, there were 4 heads, and the relative frequency is 0.8. And in the 10th toss, the relative frequency was 6, and the relative frequency was 6 divided by 10, 0.6. Right, so now we need to look at the data here. we need to count how many more heads there were. Let's divide the data up into sections of 5 tosses because that's how they've done it in the table. So every 5, draw a line. Now we have 6 heads already. So here now we have 7, 8. So after 15 tosses, we have 8 heads. And 8 divided by 15 tosses will give you your relative frequency. Continuing, we have 8 so far. 9, 10, 11. Now we have 11 heads. 11 heads divided by 20 tosses will give you your relative frequency. Next, we have 11, keep counting, 12, 13. Now we have 13 heads. 13 heads out of 25 tosses, and that will give you your relative frequency. I'd like you to pause the video and complete the rest of the table, including the division to find the relative frequency. Resume the video when you're ready to check your work. We're on page 56 now with number 5. From the table above, complete the graph to the right using the relative frequency of heads so far for the total number of tosses, 1, 5, etc. This is just what we did on the previous page, so I'd like you to pause the video and go ahead and complete your graph. When you're done, resume the video to check your work. Question 6. What do you notice about the changes in the relative frequency of the number of heads so far as the number of tosses increases? So here we have 1 toss and we have 1 is the relative frequency because 1 head over 1 toss is 1. Had that been a tail, that data point would be down here at 1 toss and 0 heads. Then in the next toss, a tails happened. So now it was lowered because we've had less heads divided by more tosses. So notice what's happening with your data line. It starts up here and then it goes down and it sort of levels off right around the halfway mark. See how that levels off? What do you notice about the changes in relative frequency in the number of heads as far as the number of tosses increases? The relative frequency changes less and less as the frequency increases. The line appears to level off at approximately 0.5. Question 7. If you toss the coin 100 times, what do you think the relative frequency of heads would be? I believe it would be approximately 50. Think about this. If the relative frequency of heads was 50 after 100 tosses, what would the relative frequency be after 101 tosses? Would it be the same or would it be different? Does it matter if you get heads or tails? Well, remember that after every toss, the relative frequency will change, no matter if you get heads or tails. The relative frequency will change after every toss because your denominator changes. It's increasing by 1 with each toss. Question 8. Based on the graph and the relative frequencies, what would you estimate the probability of getting heads to be? Explain your answer. I estimate 0.48 based on the experiment of 40 tosses. The line hovers right around 0.5. So how close is your estimate to the theoretical probability of 0.5? 0.48 is estimated comparing to the 0.5, which is the theoretical. It is 2/100ths off. It is very close. Would the estimate of this probability have been as good, meaning as close, if Beth had only tossed a coin a few times instead of 40 times? The estimate would not have been as good, meaning as close to the theoretical probability, with fewer tosses. The more tosses you have, the closer the estimated probability will match up with the theoretical probability. The value you gave in example 8 is an estimate of the theoretical probability and is called experimental or estimated probability. So the value I gave was 0.48, and that is called the experimental or estimated probability. And that is what is the probability based on the experiment. We're going to continue to the summary. We will do exercises 1 through 8 in class. Please skip ahead in your book, and the summary is located on page 60. In this lesson, you have learned theoretical probability is based on the number of possible outcomes. Estimated or experimental probability is based on the results of an experiment. The larger the number of trials in the experiment, the closer the estimated probability will be to the theoretical probability.